Welcome back. In this video, you'll learn how to find a power series to represent a function. Let's get to it. Alright, so previously we've established that power series represent functions of x and that we can determine their interval of convergence, which are the values of x for which that function is defined for. And so we know that power series represent functions, but can we take a given function and find a specific power series to represent that function? Well, there's actually several ways that we can do this, but it's going to depend on the form of the function that we want to represent as a power series. And so we're going to look at the most common form of a function that can be represented with a power series, which is a function that closely resembles the sum of a geometric series. And so if you remember, a geometric series is a series where we have the sum from n equals 0 to infinity of some constant multiple a times r, the common ratio, to the power of n. And if that geometric series converges, meaning that the absolute value of r, the common ratio, is less than 1, then that series has this sum. The sum of a converging geometric series is the value of a divided by 1 minus r. Alright, but if we let r equal x and a equal 1, then we would have the following power series. We would have the sum from n equals 0 to infinity of 1 times x to the power of n, right? A is equal to 1 and r is equal to x, but 1 times x to the power of n is just x to the power of n, so I'll rewrite that. We'll have x to the power of n, and given that the absolute value of x, which is r, is less than 1, this power series converges, and so the sum of the series would be equal to a divided by 1 minus r, which would be 1 divided by 1 minus x. All right, and that is our function f of x that this power series represents, or at least it represents it for the values that it is convergent for. So in this case, that's f of x, but just when the absolute value of x is less than 1. In other words, when x is less than 1, but greater than negative 1, or we could write that with interval notation to be negative 1, comma 1. Okay, so this power series represents this function, f of x, for the values from negative 1 to 1. And the form of this function right here is what I'm referring to when I talk about functions that are in the form that closely resembles the sum of a geometric series. Right? We have 1 divided by 1 minus x, or a divided by 1 minus r. And so what we can do is apply this same procedure to other functions that are in a form similar to 1 divided by 1 minus x. And we're going to be able to do that by just using some algebraic manipulation techniques that we have learned in the past. But the way that we will manipulate a function into this form of a geometric sum is going to depend on where we want the power series to be centered, as well as what other features does our function have that we're going to need to change so that it's in this form, right? We have to have some constant in the numerator divided by 1 minus some common ratio r that is going to involve x in some way. In this case, this power series was centered at 0, right? We just have x to the power of n. There's nothing being added or subtracted to x, and so our common ratio r was just x. But if our power series was instead centered at 1, this part of the series would be x minus 1 to the power of n, and so we would be looking for x minus 1 to be our common ratio. We would want to have 1 minus the quantity x minus 1, because then this function would be in the form of a geometric sum for that series. Okay, so that's a general premise of what we're going to do, and so this is going to be best demonstrated by just going through an example problem of representing a function as a power series. Alright, so here's our first example. We want to find a power series for f of x is equal to 2 divided by 1 minus x cubed. Specifically, we want this power series to be centered at c equals 0, and we want to determine the interval of convergence. Alright, and so what we want to do is represent this function right here as a power series centered at c equals 0. And so what do you notice about the form of this function? Well, it's very similar to the form of the sum of a geometric series, right? We have f of x is equal to 2 divided by 1 minus x cubed. And the sum of a geometric series is a, some constant, divided by 1 minus r. So if we compare this to our function here, we would say that a is equal to 2 and r is equal to x cubed, right? We have some constant in the numerator, and then we're dividing by 1 minus some common ratio r. And so we would say that a is equal to 2 and r is equal to x cubed, and so we could rewrite our function to be in the form of a geometric series, or more specifically, a geometric power series. All right, so remember, the form of a geometric series is the sum from n equals 0 to infinity of a times r to the power of n. In this case, a is 2 and r is x cubed. So what we will have here is 2 times x cubed to the power of n. We have a times r to the power of n. Okay, and so if we simplify a little bit, remember that raising a value to an exponent can be simplified by multiplying those exponents. So 3 times n is 3n. So we would say that this is equal to the sum from n equals 0 to infinity of 2 times x to the power of 3n. And this right here is a power series that represents this function f of x. Okay, and it is centered at c equals 0 because x does not have any constants being added or subtracted from it. We just have x raised to some power. Okay, and that was true in this function right here. We just had x cubed. We didn't have x minus 1 cubed or x plus 2 cubed. It was just x cubed, so we didn't really need to change anything about this function. We could just directly rewrite that as a geometric power series, which is what we have right here. Okay, and so one more thing that we need to find yet is the interval of convergence, right? And so since this is a geometric power series, we can easily determine the interval of convergence by working with the common ratio r, right? We know that the common ratio is x cubed, and for a geometric series, we know that it will converge when the absolute value of r is less than 1. So in this case, the absolute value of r would be the absolute value of x cubed, and that needs to be less than 1. And if we remove these absolute value bars, what this statement is saying is that x cubed needs to be greater than negative 1 and less than positive 1. Okay, and so if we solve for x here to see what values of x this power series is convergent for, we need to take the cubed root of each part of this statement. So the cubed root of x cubed is just x, the cubed root of 1 is 1, and the cubed root of negative 1 is just negative 1. Right, so if we take the cubed root of each part, what we will find is that x needs to be less than 1 and greater than negative 1. And that can be represented in interval notation to be negative 1, comma 1, and that is our interval of convergence for this power series. Okay, and so this was a very basic example of how we could take a function that is in the form of a geometric sum and rewrite that function as a power series that is only defined for a certain interval of values of x that make that power series convergent. Okay, and so now let's take a look at another example where we have a function that we want to represent as a power series, but we're going to want to find a power series that is not centered at 0, but some other value. Okay, so here's our second example. We want to find a power series for f of x equals 1 divided by x centered at c equals 1 and determine the interval of convergence. Okay, so our function f of x is equal to 1 divided by x, and we want this function to be in the form of a geometric sum such that we can rewrite it into a power series that is centered at c equals 1. Okay, so what we want here is our function to be in the form of a divided by 1 minus r. But in this case, r is not just going to be x, right? Instead, this power series will be centered at c equals 1, and so we want r to be x minus 1, right? So the form that we're looking for here is some constant a divided by 1 minus the common ratio of x minus 1. This is the form that this function needs to be in order to rewrite it as a power series centered at c equals 1. Okay, because remember, there are two forms for a power series. There's the simplest form, where we have the sum from n equals 0 to infinity of x to the power of n times some term a sub n, or we can have the sum from n equals 0 to infinity of x minus c to the power of n times a sub n, right? This form is when the power series is centered at 0, and this is the form when the power series is centered at some other value c. In this case, we want c to be equal to 1, which is why we want x minus 1. Okay, so this is our end goal. We want to rewrite this function to be in this form of a power series. Okay, and so what can we do to manipulate this function such that we have 1 minus x minus 1 in the denominator? Well, what we're going to have to do is change how this function looks without actually changing the value of the function. All right, so all we can do is either multiply by a form of 1 in some way, because multiplying by 1 doesn't change a value, or we could add 0 to the denominator, right? Adding 0 to a denominator is not going to change the value of the function, and so what we can do here is add 0 to the denominator in the form of 1 minus 1, right? So we're going to have x plus 1 minus 1. This does not change the value of this function, right? X plus 1 minus 1 is still just x because 1 minus 1 is 0. We are adding 0 to this denominator. 1 and negative 1 would cancel each other out and leave us with 1 divided by x. But now by adding 1 and negative 1, what we can do is reorder this denominator such that it will be close to this form that we want, right? So what I'll do is rewrite this to be 1 divided by 1 plus x minus 1. Okay, so I moved this 1 to the front, so we have positive 1 plus this x, because that x is positive, and then we have minus 1. Okay, so I just switched x and 1, so now we have 1 plus x minus 1. And now you can see that we are closer to being in this form. We want 1 minus x minus 1, but what we have here is 1 plus x minus 1. And so now what can we do to get this function in this form? Well, remember that two negatives make a positive. So what we can do here is rewrite the function in this way. We will have 1 minus these two terms, but make them both negative. Or another way to write that is to put x minus 1 in parentheses and then put a negative in front of it. Right? If both of these two terms are being multiplied by negative 1, and we're subtracting that, those two negatives would cancel out, and we would have 1 plus x minus 1. And so we are allowed to rewrite that plus sign as being minus the negative version of those two terms. Okay, and so now what we have here is a constant divided by 1 minus some common ratio r, right? If we put parentheses around that whole part, that is going to be our common ratio r. We wanted our function to be in this form where we have x minus 1 within that common ratio, and we now have that. It's a negative, but we still have x minus 1 in our common ratio, which was what we wanted. It's always going to be okay if that quantity that we want, in this case x minus 1, is multiplied by some constant, such as negative 1. That is completely fine for us to have. Okay, so if I clean up my work here, we would say that for this function, if we're comparing it to the form of a geometric sum, that a is equal to 1 and r is equal to negative x minus 1. All right, and so we could rewrite this function to be the sum from n equals 0 to infinity of a times r to the power of n, which will be 1 times negative x minus 1 to the power of n. All right, so I'm going to replace a and r with what they're equal to. A is just 1, so we have 1 times r, which is negative x minus 1 to the power of n. Okay, now we can simplify this a little bit. If we take each part to the power of n, we could take negative 1 to the power of n, right? This negative in front of the quantity is the same as just multiplying negative 1 by each of these terms. So we could rewrite this negative to be negative 1 times that quantity. And so if we take each part to the power of n, we will have that this is equal to the sum from n equals 0 to infinity of negative 1 to the power of n times x minus 1 to the power of n. And now we have a power series that represents our function that is centered at 1. All right, so we were able to manipulate this function by adding 0 to the denominator in the form of 1 minus 1, and then we were able to rewrite it into this form that could be rewritten as a geometric power series that then led us to our final answer of a power series centered at 1 that represents that function. Now, the only thing that we need to do yet is determine the interval of convergence. And so remember, our geometric power series will converge when the absolute value of r is less than 1. So in this case, r is equal to negative x minus 1. So we'll have the absolute value of negative x minus 1, and that needs to be less than 1. And so these absolute value bars are going to eliminate this negative sign. So what we really have here is the absolute value of x minus 1 less than 1. And that means that x minus 1 needs to be less than 1 and greater than negative 1. Okay, and so then to solve for x, we need to add 1 to each part. And so negative 1 plus 1 is 0. X minus 1 plus 1 is just x. So 0 is less than x, which is less than 1 plus 1, which is 2. And so when x is between 0 and 2, this power series that represents our function will be convergent. In other words, this power series represents this function only for the values of x from 0 to 2. Okay, so 0 to 2 is the interval of convergence for this power series. Okay, and now one more thing to note, I don't think I mentioned this in the previous example, but once you get to the point where you have the absolute value of x minus c, whether that's just the absolute value of x because c is equal to 0, or you have x minus some value, as soon as you have the absolute value of that, whatever that value is less than, that is going to be the radius of your interval of convergence. Okay, so since the absolute value of x minus 1, which is the common ratio for our geometric power series, and it's less than 1, the radius of our interval of convergence is 1. And you can see that that's true, right? This power series is centered at c equals 1, and 0 and 2 are both 1 value away from 1. 1 minus 1 is 0, and 1 plus 1 is 2. Okay, so if you wanted to make a note of that, you could say that the radius is equal to 1, and I believe that was true for our previous example as well, where our interval was from negative 1 to 1, and it was centered at 0, so the radius would have been 1. Okay, so just note that you could also find the radius in your work when you are trying to find the interval of convergence. Okay, and so with that, let's take a look at another example. All right, so next up, we want to find a power series for the function f of x is equal to 1 divided by 4 minus x, centered at c equals 0, and we want to determine the interval of convergence. Okay, so this time, our function is f of x is equal to 1 divided by 4 minus x. And in order to write this as a power series, we want this function to be in the form of the sum of a geometric series. So we're looking for some constant a divided by 1 minus r. And r is always going to involve x. And so since we want a power series centered at c equals 0, or just centered at 0, the common ratio r needs to just be x. All right, so in this case, we're just looking for x. And we already have that. If you look at our function, we have 1 divided by 4 minus x. We already have the common ratio that we want. However, this function is not quite in the form of this geometric sum, right? We need a constant divided by 1 minus the common ratio, not a constant divided by 4 minus the common ratio. And so what we have to do here is manipulate our function in a way such that we will have 1 minus the common ratio. Okay, and so what we can do to achieve that is multiply by a form of 1. All you have to do is ask yourself, what can we multiply by 4 to make it 1? Well, 4 times 1/4, or if you take 4 and divide it by 4, it will become 1. So we will multiply by a form of 1 of 1/4, right? We're going to have 1/4 divided by itself, and we're going to multiply that by our function, and that will not change the value of the function because 1/4 divided by itself is equal to 1. All right, you can always multiply by a form of 1. It's not going to change the value of your function. But if we go ahead and multiply this into our function, what we're going to have is that this is equal to 1/4 divided by 1 minus x divided by 4, right? 1/4 times 1 is 1/4, 1/4 times 4 is 1, and 1/4 times x is x divided by 4. Okay, and so now our function is in the form of the sum of a geometric series. We need to have some constant divided by 1 minus the common ratio, which needed to involve x, not x plus 1 or x minus 1, just x. And of course, that can be multiplied by any constant multiple. In this case, we have 1/4. That doesn't matter. We just needed to have x without any added or subtracted constants. Okay, so we have a constant of 1/4 divided by 1 minus a common ratio involving just x. And so, in this case, we would say that a is equal to 1/4 and r is equal to x divided by 4. And so we can rewrite our function to be the power series from n equals 0 to infinity of a, which is 1/4, times r to the power of n. And r is x divided by 4, and so we'll raise that to the power of n. Okay, and so now we can simplify this power series a little bit. We'll raise x to the power of n and 4 to the power of n, and watch what happens when we do that. We'll have the sum from n equals 0 to infinity of 1 divided by 4 times x to the power of n divided by 4 to the power of n. Now we have 4 and 4 to the power of n in the denominator that we can combine by adding their exponents. Right, when you have two values with the same base, let's say we have x squared and x cubed, and we're multiplying them, the result of that can be found by adding their exponents. So this would be equal to x to the 5th power because 2 plus 3 is 5. In this case, we have 4 to the 1st power times 4 to the power of n, so we can combine this by adding their exponents. So we'll have 4 to the power of n plus 1. Okay, and so this will be equal to the sum from n equals 0 to infinity of x to the power of n divided by 4 to the power of n plus 1. That is the power series that is centered at 0 that represents this function. Okay, and so one more thing that we need to determine is the interval of convergence. So remember, this geometric power series will converge when the absolute value of r is less than 1. And so in this case, r is equal to x divided by 4. So we have the absolute value of x divided by 4 is less than 1. And the absolute value bars only need to be around x, right? They don't need to be around 4 because 4 is always going to be positive. And so if we have the absolute value of x divided by 4 is less than 1, we can multiply both sides by 4 and have that the absolute value of x is less than 4. And at this point, we can determine that the radius of convergence will be 4 because we have the absolute value of x, which is the part involving x raised to the power of n in our series, and it's less than 4. So the radius of convergence is 4. And so I'll make a note of that. R is equal to 4, okay? And then the interval of convergence will be from -4 to 4 because the absolute value of x less than 4 implies that x is less than 4 but greater than -4, okay? And so I'm going to write the interval of convergence over here. It will be from -4 to +4. That is the interval of convergence for our power series that represents this function. Okay, and so that's how we can represent this function as a power series centered at 0, but what if we wanted to represent this same function as a power series, but a power series centered at a different value? Let's say we wanted it to be centered at 1 instead. How would we go about finding that power series? Well, since we're going to want the power series to be centered at c equals 1, we want our function to be in the form of a divided by 1 minus r, where r involves x minus 1, right? If our power series is going to be centered at c equals 1, the common ratio r will need to be x minus 1, so that when we rewrite our function as a power series, we will have x minus 1 to the power of n. And of course, any constant multiples multiplied by both of these terms is fine, as long as we have x minus 1 in some way. All right, and so how are we going to do that for this function? Well, the process is going to look a little bit different than it did when we wanted our power series to be centered at c equals 0, because now we need to manipulate our function in a way such that we have x minus 1. Or another way to look at it is we would want a divided by 1 minus x minus 1, and so if you distributed that negative through this quantity, this would be equal to a divided by 1 minus x plus 1. Okay, so we could also try to get the denominator of our function in this form of 1 minus x plus 1. So if I write down our function, f of x is equal to 1 divided by 4 minus x, we want to find a way to get our function in this form, to have some constant divided by 1 minus x plus 1. so that we can rewrite it to be 1 minus x minus 1, which would result in a power series centered at 1. All right, and so what can we do to the denominator of this function to get it in this form? Well, the first thing that we want to do is form the x minus 1. In other words, we want to get this negative x and positive 1. And so how are we going to do that? Well, we could do the method from before, where we add 0 in the form of plus 1 and minus 1, but an easier way to do that in this case is just to split up this 4 into two different values, right? 4 is equal to 3 plus 1, so we could rewrite this function to be 1 divided by 3 plus 1 minus x, right? Now we have a positive 1 and a negative x that would form negative x plus 1. So if we reorder these terms, this would be equal to 1 divided by 3 minus x plus 1, which is close to what we want to have in our denominator, right? We want to have 1 minus x plus 1, and we have most of that, right? We have minus x plus 1. This 3 is the only part that doesn't match. We have a 3 minus x plus 1 instead of a 1 minus x plus 1, and we'll work on that next. But first, I'm going to pull this negative out of each of these terms so that we have minus the quantity x minus 1. Right, so this will be equal to 1 divided by 3 minus x minus 1. All right, so we're almost there. Our function is almost written in a form that we can rewrite as a geometric series. The only thing we need to change is that value of 3. We need that to be 1. And so what we can do to achieve that is multiply by a form of 1 of 1/3 divided by itself, right? If we multiply by 1/3 divided by 1/3, we'll have 1/3 in the numerator, and this 1/3 multiplied by 3 will create a 1 minus x minus 1 times 1/3. All right, so if I clean up my work here, if we go through with this multiplication, we will have that this is equal to 1/3 divided by 1 minus 1/3 times x minus 1. Okay, so 1/3 times the numerator, which is 1, will be 1/3. 1/3 times 3 is positive 1. And then 1/3 times this quantity will be 1/3 times x minus 1. And so now we have manipulated our function into the form of the sum of a geometric series, and so we can rewrite it as a geometric series. In this case, a is equal to 1/3, and r is equal to 1/3 times x minus 1. Right? This whole part that we are subtracting is the common ratio r for our geometric power series. Okay, we have the x minus 1 that we wanted, but it's multiplied by 1/3, which is okay. We can have it multiplied by a constant, that's no problem. As long as we have that x minus 1 quantity, we're going to be fine. And so our power series will be equal to the sum from n equals 0 to infinity of a, which is 1/3, times r to the power of n. So we'll have 1/3 times x minus 1 to the power of n. This is the power series centered at 1 that represents this function. But we can simplify it a little bit to make it a nicer power series to look at. So if I clean up my work, we can take each of these parts to the power of n. So we'll have 1/3 to the power of n and x minus 1 to the power of n. And this will be equal to the sum from n equals 0 to infinity of 1/3 times 1/3 to the power of n times x minus 1 to the power of n. Now 1/3 to the power of n will just be 1 divided by 3 to the power of n, because 1 to the power of n, as long as n is finite, is just 1. And so I'll just rewrite this, and we will have 1 divided by 3 to the power of n. Okay, and now we can combine these denominators. 3 times 3 to the power of n will be 3 to the power of n plus 1, because we add the exponents. And so we can rewrite this power series one more time to be the sum from n equals 0 to infinity of x minus 1 to the power of n divided by 3 to the power of n plus 1, right? We just have 1 in the numerator, so we can multiply this into the numerator, and then in the denominator, we have 3 to the power of n plus 1. Okay, and so this is our power series centered at 1 that represents this function. Now all we have to determine is the interval of convergence. And so remember, r is equal to 1/3 times x minus 1, and the absolute value of r needs to be less than 1 for the power series to converge. So if we look at the absolute value of r less than 1, we will have the absolute value of 1/3 times x minus 1 less than 1. And this 1/3 will not be affected by the absolute value bars since it's already positive. And so I'm just going to rewrite this to be 1/3 times the absolute value of x minus 1. And now we can multiply both sides by 3 to eliminate this 1/3. And so we'll have the absolute value of x minus 1 less than 3. All right, and at this point, we can determine the radius of convergence because we have x minus 1, the part of our power series that's raised to the power of n, or the part that involves the variable of x, and it's less than 3, and so our radius will be equal to 3. All right, so you can make a note of that if you want, but the absolute value of x minus 1 less than 3 implies that x minus 1 is less than 3, but greater than negative 3. And so then if we add 1 to each part of this statement, negative 3 plus 1 is negative 2. So we will have this, negative 2 is less than x. X minus 1 plus 1 is just x, and that will be less than 3 plus 1, which is 4. And so when x is between negative 2 and 4, this power series converges. So our interval of convergence is from negative 2 to positive 4. That is the interval of convergence for the power series centered at 1 that represents this function. All right, and so that's our final answer. And so now let's look at one more example of representing a function as a power series. All right, so here's our last example. We want to find a power series for f of x is equal to 5 divided by 2x minus 3 centered at c equals negative 3. All right, so this one's going to put all of our skills together. Everything that we have used thus far in our other examples is going to come into play here. The first thing that you need to notice is that this function is similar to the form of the sum of a geometric series, but we're going to need to manipulate it in order to represent this function as a power series. All right, so this time we're working with f of x is equal to 5 divided by 2x minus 3. And we want it to be in the form of a divided by 1 minus r, where in this case, our power series is centered at negative 3. And so r needs to include x plus 3 in some way, right? The general form for a power series is x minus c. And so if we're centered at negative 3, we would have x minus negative 3, which is x plus 3, okay? But I want you to notice something about our function. We have 2x minus 3. So when you have a constant multiple in front of x, you need to remember to take that into account for what your common ratio will be equal to. In this case, we're going to want that 2 to be multiplied by x plus 3. We want to be able to pull out a common factor of 2 from x and some constant to have this quantity of x plus 3 within our function. All right, so if we distribute 2 through this quantity, we're going to have 2x plus 6, right? 2 times x is 2x, and 2 times 3 is 6. And so we want to form 2x plus 6 in our denominator. All right, and so that's going to be the first thing we want to work on. We want to form this 2 times x plus 3 as our common ratio. All right, and so how are we going to get 2x plus 6 in this denominator for our function? Well, what we can do is add 0. We can add 6 and negative 6, right? So if I do that, this will be equal to 5 divided by 2x minus 3 plus 6 minus 6, right? 6 minus 6 is 0, so we are adding 0 to the denominator. It's not changing the value of the function. And now we can reorder our terms to have 2x plus 6. So if we do that, this will be equal to 5 divided by negative 3 minus 6 plus 2x plus 6. All right, so I just reordered our terms. Now we have 2x plus 6 in the denominator, just like we want. And we have negative 3 minus 6, which will combine to be negative 9. So this is equal to 5 divided by negative 9 plus 2x plus 6. Okay, so now we're a little bit closer to getting this function in the correct form of the sum of a geometric series, but we have a little bit more work to do. We need this negative 9 to be positive 1, and we need to be subtracting that common ratio, right? We need to have 1 minus r. And so the first thing I'm going to do is work on getting this negative in play. And that's going to be the easiest part, because all we have to do is rewrite this plus sign as 2 negative signs, right? And so let me clean up my work and then I'll show you what I mean. Since subtracting a negative value results in a positive value, what we can say is that this is equal to 5 divided by negative 9 minus the negative quantity of 2x plus 6, right? So if we group these two terms together, make them negative, and subtract that whole quantity, that is the same as adding both those terms. All right, and so if we put parentheses around that whole part, then we can see that our common ratio R will be negative quantity 2x plus 6. All right, it doesn't matter that it's negative. We have 2x plus 6 in some form, which already involves x plus 3, which is what we need for the power series to be centered at negative 3. Okay, in fact, if we pull out that 2 from each of these terms, what we'll have is 5 divided by negative 9 minus negative 2 times x plus 3. All right, so we pull 2 out of x, so we just have x, and we pull 2 out of 6, so we have 3, and now we have negative 2 times that quantity. This negative was already being multiplied by both of these terms, but now we pulled out a 2, so now we have negative 2 times x plus 3. And so we have x plus 3, which is what we want in order to rewrite our function as a power series centered at negative 3. Okay, so now we're almost there. Our function is almost ready to be rewritten as a power series. The only thing we have left to do is change this negative 9 to be a positive 1, right? We need to have 1 minus the common ratio. So this needs to be 1 minus this common ratio. All right, so if I clean up my work again, what we can do to make this negative 9 positive 1 is divide the numerator and denominator by negative 9. Or another way to view that is to multiply by a form of 1 of negative 1/9 divided by itself. All right, and so if we do that, we'll have that this function is equal to negative 5/9 divided by 1 minus positive 2/9 times x plus 3. Right, so negative 1/9 times 5 is negative 5/9. Negative 1/9 times negative 9 is positive 1. And then negative 1/9 times this quantity, we'll just multiply it by the negative 2, since everything's being multiplied together. And so negative 2 times negative 1 is positive 2, and then we're dividing by 9, so we have positive 2 divided by 9. Okay, so those two negatives cancel out, and so we have positive 2/9 times x plus 3. Okay, and so now our function is in the form of the sum of a geometric series that we can use to rewrite our function as a power series. In this case, a is equal to negative 5/9, and r is equal to 2/9 times x plus 3. All right, that is the common ratio that is being subtracted from 1, and negative 5/9 is the constant in the numerator. So our power series will be the sum from n equals 0 to infinity of a, which is negative 5 divided by 9, times the common ratio to the power of n. So we'll have 2/9 times x plus 3 to the power of n. Okay, now if I clean up my work again, we can simplify our power series by taking 2/9 to the power of n and x plus 3 to the power of n. So this is equal to the sum from n equals 0 to infinity of negative 5/9 times 2/9 to the power of n times x plus 3 to the power of n. But we can rewrite 2/9 to the power of n by taking each part to that power. So we'd have 2 to the power of n divided by 9 to the power of n, which will allow us to simplify further, right? So we'll have 2 to the power of n divided by 9 to the power of n. And now we have 9 times 9 to the power of n in the denominator, so we can add their exponents and have 9 to the power of n plus 1. And so we can rewrite our power series one more time. We'll have the sum from n equals 0 to infinity of negative 5 times 2 to the power of n times x plus 3 to the power of n divided by 9 to the power of n plus 1. And so that is our power series centered at negative 3 that represents this function. All right, but we still need to find the interval of convergence. This power series only represents this function for a certain interval of x values. So in order to find that, we need to look at the common ratio. When the absolute value of r is less than 1, the geometric power series will converge. All right, so we're going to look at the absolute value of r less than 1. In this case, that will be the absolute value of 2/9 times x plus 3, because that's what r is equal to. And the absolute value bars are not going to affect 2/9, so we can pull that outside of the absolute value bars because 2/9 is already positive. And so we'll have 2/9 times the absolute value of x plus 3. And now if we divide both sides by 2/9 or multiply both sides by 9/2, the reciprocal of 2/9, we will have that the absolute value of x plus 3 is less than 9/2. And now at this point, we have the absolute value of x plus 3, which is the part of our power series involving x that is raised to the power of n. And so, since that is less than 9/2, we know that the radius is equal to 9/2. All right, so the radius of our interval of convergence is 9/2, so we can write that down. And the absolute value of x plus 3 is less than 9/2, implies that x plus 3 is less than 9/2, but greater than negative 9/2. And so now we need to solve for x by subtracting 3 from each part of this statement, but I'm going to need a little bit more room. So if I clean up my work a little bit, subtracting 3 from each part would be the same as subtracting 6/2, because 6 divided by 2 is 3. All right, so negative 9/2 minus 6/2 would be negative 15/2, and that will be less than x, which is less than 9/2 minus 6/2, which will be 3/2. All right, and so when x is between negative 15/2 and 3/2, this power series will be convergent. This power series centered at negative 3 represents this function for the interval of x values from negative 15/2 to positive 3/2. That is our interval of convergence, and that is it for this example. All right, and so with that, this was the last example for this video. And so if you want to see more examples of representing functions as power series, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I have for now. So I will see you next time.